So we're looking at the spring mass system that's free, so no external driving force. We get a homogeneous equation, and damped in that we have this resistive force. We get our differential equation there. Two auxiliary roots to the two roots to the auxiliary equation, and we looked at the situation where we get an overdamped system, two distinct real roots, a critically damped system with one repeated real root, and now we'll consider the case of two complex conjugate roots. And that will be the underdamped system that we see here. In this case, we get this general solution. Okay, we could combine the cosine and sine here, as we've discussed before, using these relations there. And sometimes a e to the lambda t is called the damped amplitude, and this is called the quasi-frequency, and this the quasi-period. And the reason being is that with these underdamped systems, what you generally get are oscillations that die out, okay? Or we could see over here, okay? So let's look at an example. A mass weighing 16 pounds is attached to a 5-foot long spring. At equilibrium, the spring measures 8.2 feet. If the mass is initially released from rest at a point 2 feet above the equilibrium position, find the displacement. Okay, this x of t, so find the solution. If it is further known that the surrounding medium offers a resistance numerically equal to the instantaneous velocity. That part here gives us beta equals 1. These are the initial conditions that we read. Now, this 8.2 is when the spring is stretched, okay, at equilibrium with this 16 pounds applied from this mass, okay? So that's L plus S, actually, where S is this extra stretching that occurs due to gravity. L is 5 feet. That's the natural length of the spring. And so this S is 3.2 feet. Why do we want that? Well, we want K. And to get K, we have to apply a force. We're going to apply a force of 16 pounds. And over the extension, 3.2 feet beyond the natural length, we get 5 pounds per foot. Something that's just important here is, even though we may think of pounds as kind of like a mass, it's not. Okay, this is a weight. This is a force. Pounds are force. So that, be very clear on that a pound is a unit of a force. Okay, that could get confusing because, mass is measured in kilograms, and we could think about the weight somewhat like the mass in the US, but it's not. Okay, pounds is a force. So the mass then is the weight over gravity. Gravity here, the acceleration of due to gravity is 32 feet per second squared. You get half a slug, okay? And so we got our parameters. We plug them into our differential equation. Well, here goes our differential equation. We solve. We get, and notice something here. I should point out that lambda squared minus omega squared is 0. But here we flip it around to omega squared minus lambda squared. Why? It's because we don't want to deal with another I. Okay, we take into account the I by using the cosine and sine. Okay, so the cosine and sine deal with that problem of having complex conjugate roots. And now we just flip them around so that we don't get any negative number in the square root, because we've already taken into consideration that we are getting a negative number in the square root of these terms here. Okay, so we just flip them around. Notice that in the solution that we flip these around. Anyway, so we get our roots from the auxiliary equation. we get our general solution, we apply our initial conditions, okay, and we fix the constants, and we get this solution. And notice that you could think about the oscillations dying out exponentially, okay. So this term here, this is kind of like the envelope around, okay, and this term here deals with the oscillations that go around in that envelope. And that's how our system that is underdamped looks like.